Hi everyone. So my name is Garvit and I'm the founder and CEO at Electron. And we are building a proof aggregation layer. And what that is and why it's that important, we'll learn today. So the talk is divided into two parts. In the first one, we'll just go through a high-level overview, try to understand the problem statement and how we are solving that. And in the next part, we'll try to take a deeper dive, probably on the technical side as well. So let's get started. So the so let's start with the problem statement that no one talks about in ZK. Most companies are focusing on the proving side performance. And however, if you are a ZK project and the cost of verifying a proof on Ethereum is super high, it costs like $30 to verify one proof. And if you analyze that, so if you're verifying one ZK proof inside every Ethereum block, this will cost you like $100 million every year. This is not practical by any standards unless you are a very large rollup where you can subsidize this cost amongst a large number of users. You cannot afford to pay this, and that's why you'll see most of the B2B use cases of ZK are not on mainnet. For example, co-processors is a good example. Like you won't see them on mainnet a lot. In fact, ZK projects already had to spend 60 million in the last 3 years in proof verification on Ethereum. And this is just Ethereum. If you start expanding this to Bitcoin and other layers, this will be even more expensive. Furthermore, if you look at the cost split of running any ZK project, the biggest cost center is actually the proof verification. Again, no one mentions this. You will see every single company talk about the proving side of things. Proving side performance, ZK VM, ZK rollups, hardware companies, they're all focused on that. No one solves this problem, and in my opinion, Electron is the only one that has made any significant strides in solving this problem so far. Furthermore, if you look at the next couple of years, the underlying L1s will only get more expensive with time. But the proving side performance will improve and it will get cheaper. So this graph, this pie chart will get even more skewed towards proof verification, and proof verification is likely to occupy like 80% of the overall cost of operating a ZK project. So this is where we come in. We reduce the cost of verifying proofs on Ethereum by 95%. And the way we achieve this is by collecting ZK proofs from multiple ZK projects and aggregating them into a single superproof. And that superproof is then submitted to Ethereum or any L1 of choice, which leads to these projects sharing the cost of this proof verification on Ethereum. So cost amortization is how we do this, achieving a 95% reduction in verification costs. This is not some theoretical protocol that we will ship a year from now. This is live today in a production-ready capacity on testnet. We have been operating for the last 4 months, and we have aggregated proofs from some of the top ZK projects. These are live ZK proofs that were submitted by these projects on Ethereum mainnet, and we picked them up from there and ran it through our aggregation layer and aggregated them. As a result, if this testnet was deployed on mainnet in the last 4 months, we would have saved ZK projects 700,000 in gas costs in proof verification on Ethereum. And we have aggregated more than 100,000 proofs across these protocols. Not just the last 4 months, if we were live for the last 3 years, we would have saved projects 54 million in verification costs. This is the cost. So 60 million is the number I showed you earlier. That's the cost projects had to pay. And if we achieve a 90% reduction on that, you save 54 million. So this is money that is back in the pocket of the protocols or their users. If we talk about the next 5 years, this is where things get super interesting. So if you look at the Ethereum scaling roadmap, we should expect that the Ethereum block space will be primarily used for settling ZK rollups. And if we assume a 60% usage of the Ethereum block space for proof verification, that amounts to $10 billion every year on proof verification by ZK projects just on Ethereum. If you add Bitcoin and everything, this number will be much higher. Now, using Electron's proof aggregation approach, we will reduce this cost down to 500 million. So the cost that projects would have to pay would be 10 billion. Now with our technology, they only have to pay 500 million, not per project, but collectively the whole ecosystem of ZK on Ethereum will have to pay 500 million in proof verification costs. So if there are a million ZK rollups, you can divide that cost by a million. So this leads to massive cost savings, which will again be passed on to users. As a protocol, we have to be profitable, and that's why we will not pass on the entire value to the users. We have to have some revenue that we keep for ourselves. And what this number will be is something we're trying to determine. It's not that easy because we want to make sure that the cost is not too high so as to make it too expensive. At the same time, we want to capture as much value as possible. So we'll have to come up with an automated mechanism to come up with a pricing for how much value the protocol actually captures on top of the underlying cost. So this was like a quick introduction to the problem statement of high costs and the aggregation that is the way to solve it. Given that we have done that, let's move on to the next part, which is some common misconceptions that we hear about proof aggregation, and let's try to address them one by one. So the first one, I'm sure some of you have already assumed this while listening to this presentation, that okay, this seems like that aggregation must be a trade-off, that you can reduce your verification costs, but that increases your latency clearly because there's something in the middle that that you have to do as an additional step. But that's not true. We actually reduce both your cost and latency. The way we do this is, so right now the cost of verification is so high that projects can afford to settle on Ethereum once every 30 minutes or 1 hour. Okay? We reduce the cost by so much that you will be able to settle every Ethereum block, thereby reducing your settlement time or latency. So both cost and latency reduction we offer. Second, people assume that this is only needed for Ethereum. Again, not true. Bitcoin also needs proof verification. Bitcoin has an even more limited block space. Furthermore, there are data availability layers like Celestia and Goel who have massive ability to store data, but their execution capabilities are next to nothing. So they are working on adding proof verification into their base layer. And if you add aggregation on top of that, these data availability layers will essentially have infinite execution capabilities as well. The final myth that we often hear is that this comes from especially the more ZK educated folks. People assume that aggregation layers must be specific to a given proving scheme, or they must be specific to a given ecosystem. Again, not true. What we have built is a universal proof aggregation layer where all proving systems and all ecosystems are aggregated in one aggregation engine. In fact, we already support most of the popular proving schemes or ZK VMs today, RISC-0 SP1 included. And again, of course, GNARC and CIRCOM and all of that, which probably provide us more than 90% coverage of the proof generation space right now. Furthermore, it takes us less than a day to add another proving system into our aggregation layer. So if you ship Binius 2.0 or Binius 3.0 today, we will add you in the aggregation layer by tomorrow. The way we do this, and no additional audits are required on your end or our end, you simply give us the verification code that you've written as part of the proving system. We port that to our aggregation layer, and the way we have designed this is that no additional audits are required at your end or our end, as long as your verification code is obviously audited. So this was like the high-level introduction to what aggregation layers are, why they're important, and how they work in practice. I wanna now, does anyone have any questions so far? I would love to take them in the middle. Okay, so I'll just move on. Okay. Yeah.
I just had a question around, you said it only takes you a day and it requires no audit. Could you like elaborate on why?
Sure. So the way we design our aggregation layer is, so I'm trying to think of an analogy. It's like you have a host of verification, uh, proof verification code that is available inside the circuit of the aggregation layer. And whenever you send a proof, we can just use one of those already pre-existing code to verify that proof inside our aggregation layer. So as long as, we obviously have to recompile everything because we have to include that particular verification code inside our aggregation layer, but we don't have to audit it again. As long as your verification code is written in Rust, because that's what we use to power. I hope that answers the question.
Yeah, it does. Thank you.
Thank you. Okay, I don't see any more questions, so I'll move on. So let's go into, so I'm going to show you some maths, but the purpose here is not to show you math, but to actually explain you how the cost structure of an aggregation layer evolves from the day you hit mainnet till the day you're acquiring more customers. Okay. So if you assume that the cost of verifying our superproof on Ethereum is 350,000 gas, and there are n proofs that we are aggregating. So every single proof has to pay an nth slice of that superproof verification. So 350,000 divided by n is what they should ideally pay. However, since the verification will happen inside our contract on chain, you will be required to make a cross-contract access call in order to check for an inclusion proof of your specific proof inside your application. So additional 16,000 you have to pay as gas to do that. So this is the equation that represents the per proof verification cost for verifying your proof using an aggregation layer. Now if you plot this on a graph, you get a very interesting curve which falls very rapidly. So if you know this is a hyperbola, so it falls very rapidly in the beginning and then stabilizes towards the theoretical value, which is the 16,000, which is again the access cost. So this is the theoretical minimum. You can't go below that. And so when you launch aggregation layer, you're aggregating less proofs on mainnet. So you're on that side of the graph. Okay, so you're still offering a cost reduction, but it's not a very high cost reduction, like a 50% maybe. Okay, but you eventually want to get to 95%. So you keep aggregating more proofs, more protocols, and that keeps on reducing your per proof cost. The total cost of verification stays the same. And so that's how, like, you build a strategy to take your aggregation layer to production. Based on mainnet, we have already made some progress on this particular curve, and we are aggregating 8 proofs as of today, which leads to an 83% reduction in costs already. In fact, across the protocols that we are working with, we have, and some of the names that are on this list and not on this list, we have onboarded already 60% of the proof generation market on Ethereum. These names probably represent a 20 to 30% market, and we have onboarded some of more ZK VMs, and we are onboarding some of the new ones, which will allow us to be way on this side on this particular graph, which is what we want for maximum cost reduction. Okay. Finally, we were building using custom circuits until recently, but we switched to using RISC-0. And we actually did a massive analysis between all the 4 ZK VMs available out there and finally selected RISC-0 because of its performance for aggregation layers. And we just feel that the product is a lot more ready compared to other ZK VMs. One last point, or second last point rather. So the process of integration, if you are already live on mainnet and you're submitting proofs on Ethereum directly, the process of integration with us is pretty straightforward. Rather than sending your proofs directly to Ethereum, whatever RPC endpoint you use to broadcast your proofs, you just send your proofs to our RPC endpoint for our decentralized proving network. We aggregate it, send it to Ethereum on our superproof verification contract, and then you can query your application logic on chain. The contracts can query our contracts for an inclusion proof and carry on with the rest of your business logic. Again, the integration is, we have tested, it's like less than half a day for a single developer. Finally, one last thing I want to mention here. So this is an opportunity for the industry to help us out. As a aggregation layer, we operate provers, and we want to decentralize that proving. And we have decided that restaking is the best approach to decentralize that. So if you work in restaking, you can reach out to us. We are already working with one of the restaking providers on this, and you can always, we have designed this in a way where multiple restaking companies from different ecosystems, it doesn't even have to be an Ethereum restaking company, you could be restaking, I don't know, on Solana, for example, and you can still provide us liveliness guarantees as part of our prover. That's it from my side. Yeah.
Thanks, Garvit. Any questions? Please.
So in addition to proof aggregation, do you also support some kind of way to include data? So for example, like with the proof request, I can also provide some data, what I want to verify against. Maybe you can store it like in an aggregate way in blobs or compress the data.
Are you referring to public inputs for the proof, or?
Yep.
Yeah, obviously. So like when you verify a proof, you have to have the public inputs come with it. However, so the way we split this is, when we verify the proof and you consume that in your application, you can send those public inputs directly in your contract to consume those public inputs, and our contract will give you a proof that those public inputs are actually valid according to the verification circuits. Does that make sense? So to answer your question shortly, like, yes, you can send public inputs. You have to send them, otherwise how can you verify a proof? And you'll need them anyways for your application on chain. Yeah.
Thank you.
Just want to ask, do you have like a single verification circuit for all proof systems, or you have different circuits and then you do some kind of folding?
So we so think of in a very crude way. Imagine a very large circuit, which is verifying, which has a verification logic for all of these individual proof systems inside that circuit. And then when we run that code, we're essentially generating a proof that all these proofs are individually valid.
Right. So it's a big single large circuit.
In a crude way, in the actual implementation, it's actually split across multiple individual things, which are then combined in a Merkle-Tree sort of fashion for parallel, so that we can leverage parallel proving.
Right. Okay. Thanks.
Anyone else? Okay. Thank you, Garvit.